This is a video for MEI Core Pure Mathematics, Vectors 3 Equations of Lines, 3.1 the vector equation of a line in 2 dimensions. The vector equation of a straight line can be shown to be r equals a plus lambda times d. Now let's have a look at those pieces. D is the direction vector, so that's the direction of the line, a vector parallel to the line. Lambda is a multiple, we sometimes refer to that as a parameter, it's a scalar multiple of d, and a is the position of a point on the line. So if we have a line like this, we may know this point here, I'm going to call that a, and that has a position vector relative to the origin, so that's a, and the direction of this line is d. So in order to get to a point on the line, you need to go from the origin to a point that you know on the line, so that's follow A, and then step up the line by some multiple of d. And the vectors could be written as column vectors, so that's a1, a2, plus lambda lots of d1, d2, for instance, or they could be written in ij form. So r is a1 lots of I plus a2 lots of j plus lambda lots of d1 I plus d2 j. Okay, so let's have a look at the vector equation of a line. We're given here a line that passes through this point, minus 3, 2, which is here on the diagram, in the direction 2i plus j. Well, the direction 2i plus j is 2 across and 1 up, so we can see that that's what this line represents, 2 across and 1 up. I've chosen to write this as column vectors, and actually, although we can use i's and j's, predominantly you will see column vectors throughout these videos. So the position of any point on the line is go to the position you know about, the known point on the line, and add in some multiple of the direction, 2, 1. Now notice this says find a vector equation of the line, and that's because there are lots of different vector equations of this line. For instance, I could use this point here, and in which case my known point is 1, 4, and I've got the same direction. I'm going to give it a different parameter because it will take different values, but it has the same direction. So these are parallel, and although they don't look to be the same line, you can actually get to every point on this line either by starting from here or by starting from here and traveling in the same direction. Similarly, you can start from the same point but use a vector which is parallel. So let's look at one that's twice as long, 4, 2. You can look at a vector which is parallel to the direction. So again, we can get to any point on this line by going to the known point and then stepping on. And in fact, for any value of lambda here, half of that in here will give you the same point. Okay, so let's look at finding the vector equation of the line that passes through these 2 points. I'm going to call those points A and B. Well, the vector equation will be the position vector of A, let's call that A, plus any multiple of the direction from A to B. Let's look at this direction. A to B is just simply B minus A, which is 2 minus 1, take away 3, 2, which gives me minus 1, minus 3. Now, remember, this is the direction of the line, and in fact, anything that's parallel to that can be used. So I could use 1, 3 if I wanted to avoid having minus signs in both of the components. So my vector equation becomes, pick a start point, I'm going to use a 3, 2. We used it here, so we'll continue with that, plus some multiple of the direction of the line. I could use -1, -3, or I could use 1, 3. I'm going to use 1, 3 just simply because I've got fewer minus signs. I could just as easily have used 2, -1 as my starting point, or indeed any other point on the line that I happen to know about, and I could use any multiple of the direction. So, a little bit of a summary here. The vector equation of the line is not unique. Remember that you can change the known point for another point on the line, and you could use a negative version of d, so it's still parallel but in the opposite direction, or indeed any other multiple of d. The gradient of the line is given by d2 over d1, so if the direction vector is d1, d2, so if that is d1, d2 as a vector, then this height here is d2, this length here is d1, and so the gradient is just d2 over d1. Notice that two lines are parallel if the direction vectors are the same or one is a multiple of the other. And finally, you can show that two vector equations represent the same line, and we talk about collinear, if they are parallel and share a common point. So there's two bits here to establish. Let's have a look at checking that with this pair of lines. I'm going to call this first line L1 and the second line L2. And the first thing to notice is if I take this vector here, which is the direction of L1, and times it by 2, I get the direction vector of L2. So they are parallel. One is a multiple of the other. I now want to know if they share a point. So if we think about L2 for a second, we know that 3, 5 is on that line. And the question then is 3, 5 also on L1? Now for 3, 5 to be on L1, we must have a value of lambda for which -3 plus 2 lambda is equal to 3. And that would give me that lambda equals 3. So if lambda equals 3, if we think about L1, we know that r is equal to -3, 2 plus 3 lots of 2, 1. And that's equal to 3, we already know, and then 2 plus 3 is 5. So they share a point. So our two conditions are satisfied, they're parallel, and they share a point, and so therefore they are collinear. So looking at this the other way, if either of these conditions, or indeed both, are not satisfied, then they would not be collinear. The next video in this sequence is 3.2, the vector equation of a line in 3 dimensions.